Okay, let's talk about the invisible chemistry that literally builds our world. We're going to dive into hydrocarbons. These are simple but incredibly powerful molecules that are, really, the backbone of almost everything we use, from the fuel that gets us around to the plastics in our homes.
So think about it for a second. The gasoline in your car, the natural gas that might heat your home, even the plastic wrap you use for your food. I mean, they seem totally different, right? But what if I told you they all come from the exact same chemical family?
Yep, the answer is hydrocarbons. They're molecules made of just two things, hydrogen and carbon, and they form three very distinct families. The crazy part, the only thing that separates them, the one thing that gives them their entire identity, is the type of bond between their carbon atoms. That's it.
So, let's start at the beginning, with the first family. These are the stable foundation of the entire hydrocarbon world, the alkanes.
Alkanes are all about simplicity and stability. Their carbon atoms are linked together by single bonds. You can think of it like a firm, stable handshake. It's strong, it's reliable, and it's not looking to let go to grab on to anything else. It's just content.
And you can actually see this stability in their chemical formula, CnH2n+2. This basically tells us they are completely saturated with hydrogen atoms. Every carbon is holding on to as many hydrogens as it possibly can. There is literally no room for any other atoms to join the party, which is why they have such low reactivity. You could call them the calm, dependable elders of the hydrocarbon family.
So, what do we do with something that's super stable but holds a lot of energy? We burn it. This low reactivity makes alkanes the perfect fuels. Think natural gas, gasoline, and diesel. They store all that energy nice and safely until we're ready to release it. Okay, so if alkanes are the stable foundation, our next family, the alkenes, are the total opposite. They're the reactive changemakers, always looking to build something new.
The secret to an alkene's personality, the double bond. Now, instead of one handshake between carbons, imagine two. You might think that sounds stronger, but it actually creates a kind of tension. One of those bonds is just itching to break open and grab onto something new that comes along.
And that double bond makes all the difference. Their formula, CnH2n, shows they have fewer hydrogens than an alkane of the same size. This means they're unsaturated. They have open spots to add more atoms. They absolutely love to undergo what are called addition reactions, where that second bond breaks to welcome new atoms into the molecule. And we've gotten really good at taking advantage of this desire to react. Alkenes, like ethene, can be made to link together in these incredibly long chains. It's a process called polymerization. And that is how we create so many of the world's most common plastics, like the polyethylene that makes up milk jugs and grocery bags.
You can actually see this reactivity with your own eyes in a lab. It's pretty cool. If you take some brownish-orange bromine water and add it to a stable alkane, absolutely nothing happens. The color stays. But if you add it to an alkene, that double bond immediately snaps open and reacts, and the color vanishes instantly. It's this perfect visual proof of that reactive personality.
All right, now we're climbing to the very top of our reactivity ladder. If alkenes are reactive changemakers, then our final family, the alkynes, are the true powerhouses of the hydrocarbon world.
As you've probably guessed by now, alkynes are defined by a triple bond between carbon atoms. Now, this isn't just a point of tension. It's a massive concentration of energy all packed into one spot, making these molecules incredibly reactive. Their formula, CnH2n-2, tells you they are even more unsaturated than alkenes. The classic example here is ethine, which you've probably heard of by its common name, acetylene. Its reactivity is just off the charts, making it by far the most energetic of the three families.
So where on earth do you use a molecule with this much raw energy? Well, for really high-energy jobs. When you burn acetylene with pure oxygen, it creates an unbelievably hot flame. We're talking over 3,000 degrees Celsius. That's hot enough to cut right through steel. That's the power of the triple bond in action.
So, we've met each member of the family. Now let's do the fun part and put them all side by side to really see how they stack up.
This is really where it all clicks into place. Seeing them lined up like this drives home how that one simple change, from a single to a double to a triple bond, creates three completely different chemical personalities.
The whole story is right here on this one table. As we go from alkane to alkene to alkyne, you see the bonds go from single to double to triple.
At the same time, the number of hydrogens goes down and the reactivity just skyrockets from low to medium to high. And that directly dictates their use. Stable alkanes for fuel, reactive alkenes for making plastics, and the super-reactive alkynes for high-intensity welding. It's a perfect progression.
So, what's the one big takeaway from all this? It's really simple. In the world of hydrocarbons, the type of carbon-carbon bond isn't just a detail, it's everything. It decides all of it.
That simple, stable, single bond gives us the alkanes, the reliable, foundational fuels that have powered our world for more than a century.
That reactive double bond gives us the alkenes, the versatile building blocks that literally created the entire world of plastics and modern materials we rely on.
And that incredibly energetic triple bond? That gives us the alkynes, the high-energy powerhouses we use for those intense, specialized jobs that nothing else can handle.
Single, double, or triple. Each of these bonds has defined an era of technology and built the world we live in now. And that leaves us with one last question to think about. As we search for the new materials and new energy sources of the future, which bond will build the world of tomorrow?